Good morning. So I have an announcement to make first. You see it on the screen there. Our tutor, Aaron Nitz, will be running a special study session tonight, and it's in the Aspire classroom, the middle one, 3109. He's going to do that from 7 to 9. And I believe, I'm not positive, but I believe Aaron has to stop being tutor at the end of the semester. I don't know. Anyway, there's a new tutor also starting on Thursdays. So her name is Sarah Snyder. Okay. So did you have some questions you want to bring up? Let's start with that.
Can we go over limits at infinity? Like the rules behind those?
Yep.
Okay, thanks.
Okay, that sounds like the 56. Yeah, that's this this part right on the screen right now. Yeah, well, so in number 55, you have two expressions instead of just one big fraction. When you have fractions, you remember what the rule is. The fraction rule is you look at the degree of the numerator and the degree of the denominator. And if the numerator has a greater degree than the denominator and the limit is as x approaches infinity, then the answer is infinity. If the denominator has a greater degree than the numerator, then as x approaches infinity, the limit is going to go to 0. So anyway, that's the general rule. Now you look at 55 and we don't have one fraction, we have two numbers. So on 55, what's the limit of 8 as x approaches infinity? Well, 8's not affected by x. There's no x in there. So that stays the same, 8. What's the limit of 1 over x as x approaches infinity? 0. And 8 plus 0, the limit of the entire thing is 8. Let's go. I got some. Okay, let's go to 56. Okay, so here's one. What's the limit of 1 minus 4x over x plus 1? Please note the limit as x approaches negative infinity. Negative infinity. So clearly the degree on the top is 1. The degree on the bottom is 1. So we go with what? The ratio of the leading coefficients because they're tied. And that would be -4 to 1. But just to double check the signs, on top you have -4 times what? Kind of a negative infinity, which would be a positive. And on the bottom you have +1 times infinity, which would be a negative. So instead of a negative over a positive, it turns out to be a positive over a negative. Anyway, the answer is still the ratio of the leading coefficients, 4 to 1, 4. But you gotta get that sign right. So be careful when x is approaching negative infinity. Another example is 63. Okay, 63. The limit as, here we have another one, as x approaches negative infinity. I want to talk to you about that cosine x on the bottom. So as x gets negatively huge, what will happen to the cosine? And my response is not much, because as you should know by now, that cosine is forever stuck between +1 and -1, no matter what the angle is. It's always between 1 and -1. So it has little effect on the denominator. A 1 or a -1 added to an infinity or a negative infinity is just going to completely dissolve. Okay, so basically you could ignore that term. Now you can see that the degrees are tied, 1 and 1. The leading coefficients are 6 and 1. Looks like the limit's 6. Check the sign. If the top goes to negative infinity, that's going to be negative. The bottom goes to negative, it's going to be a negative, or it's going to be a +6 because a negative over a negative. You want to look at another one in that section? Yeah, let's talk about square roots. All right, look at 62. We have x cubed over square root of x squared plus 1, the limit as x approaches infinity. So what's the degree on the top? 3, right? What's the degree on the bottom? 1, because, you know, the degree of the bottom is 2, but when you take a square root, that cuts it in half. So 3, 1, obviously the numerator wins. So this is going to infinity. How about number 60? Let me grab that one, and we'll do that in the other window. So what's going to happen with that? So what's the degree on the top? 1, because it's a, you know, square root of x squared would be x. So 1 degree, first degree on the top, first degree on the bottom. The leading coefficients are 1 and negative 2. So that should go to negative 1/2. Now, hang on. What about when x approaches negative infinity? Well, on the top, what's going to happen? On the top, negative infinity squared is positive. Positive square root, that's positive. And then, so let's just, yeah. So on the bottom, x approaches negative infinity. Negative times the negative is a positive. Let's just take a look at that one in Desmos. Square root of x squared plus x. Square root of x squared plus x. And then what was the rest of that? Negative 2x on the bottom. So, and the point is, as x approaches negative infinity, right? Yeah, as x approaches negative infinity, what's going to have? So remember what we said. On top, a negative infinity substituted in here will be squared. That's going to make it positive. Principal square root of a positive is a positive. And on the bottom, a negative infinity times a negative 2 is a positive. So it looks like it's going to be positive 1/2. And if you look at Desmos, as you approach negative infinity, well, I can't go out to negative infinity, but you can see how we're getting closer to 1/2, 0.487. And, you know, no matter how far out you go, getting closer and closer to 1/2. So that makes sense. So let me put this on with a pen. Oops. You want to pick another one from that? I can't. I don't know who that was talking, but did you want to pick another one from the 55 to 64 section?
Oh no, I think I'm good. Thank you.
Okay. I'm just going to throw one more thing out, and that is that what the book, the way the book, the technique the book taught you, I didn't emphasize much, but I did show it one time. I want to take number 57 and just show you how the book does this. Okay, so let's copy that, bring it over. So here's what the book does. They say, all right, when you're taking a limit that goes to infinity, what you can do is take your expression and find the highest power of x in the expression, which in this case is x squared. Okay? Gotta get my pen working. Hang on. Anyway, take that highest power of x and divide both everything in the numerator and everything in the denominator done by x squared. And if I get my pen working, I can show you. Okay, so equals the limit as x approaches infinity. And on top, you have 2x squared divided by the highest power of x, x squared. On the bottom, we have 3x squared divided by the highest power of x, and 5 divided by the highest power of x. Okay, let me move this over. So how does this turn out? Well, on the top, the x squareds cancel, and you get 2. On the bottom, what's 3x squared over x squared? 3. And what's 5 over x? What's the limit of 5 over x squared as x squared as x approaches infinity? 0. So, I mean, the rule I taught you works also, and that is simply what? Take the highest power on top and the bottom. How do they compare? They're tied. So what do? Use the ratio of the leading coefficients. But you can also analyze these functions by dividing through by the highest power of x. I just might strike a note with some of you as a technique that could be used. All right, next question. I've got something I want to show you, so let me do that next. And that is, I wanted to talk a little bit about the mean value theorem. Okay? So remember, the mean value theorem started with this thing. You've got those 2 points that are circled here. And you can always, if you have 2 points, you can always find the slope of that line. Remember what the mean value theorem says. It says, hey, if this thing is continuous and it's differentiable in between, then there's got to be one point in between where the tangent line will have the same slope as that bottom line. Okay, so that's the theorem. Now I wanted to show you, I don't normally do this, but let's take a look at one of the problems in particular, number 15. It's an absolute value problem. And I had a student ask me yesterday, do we have to differentiate absolute value problems? Yeah, you can break an absolute value problem into the negative and the positive. You know, absolute values always have what? 2 parts because of the what? The wing shape. But here's the problem. Where's the tip? Where's the bend in this absolute value? It's when the thing inside the absolute value is 0. And that would be at x equals 5. But look at the interval. It goes from 2 to 6. So in other words, that bend is in there. Uh-oh. That means it can't be differentiated. You can't differentiate at a cusp. So notice, can't do it. Doesn't apply. The mean value theorem does not apply to problems like that. Here's another one, 16. Where the problem has 2x minus 3 times the square root of x, and the interval is from -1 to 1. Can't be done. Why not? Because notice there's some negatives involved in this interval, and when you put negatives under a square root sign, well, you can't operate. So this is not continuous. This is not differentiable. So 16 was another example. I don't know if any of you came upon that in your study, but 16, we cannot use the mean value theorem there. So I just wanted to don't like automatically, what's the key word up here in the directions? I would say it's right here. If the mean value theorem can be applied, make sure you check if it can be, because otherwise you might be exercising utility, working on a problem that you can't do. So I'm not sure I would, so anyway, just make sure of that.
So if the function isn't differentiable, you can't use the mean value theorem?
That is exact. Now, let me just say, if it's not differentiable on the interval they're asking you about.
Oh, okay.
Yeah, then you absolutely cannot use the mean value theorem. It can't be applied.
All right, thanks.
Yep. Other questions or directions you'd like me to go? I'm just going to make this comment. I just like the comment I just made. It sounds like maybe I'm hinting there'll be one like that on the test. I am not. I'm just saying that's something a person has to be on the outlook for. But remember, I've only got 50 minutes to test you guys on this whole chapter. So I'm going to go pretty much straight at the main topics. There's not going to be a lot of this exceptions. I mean, yeah, I just don't have time to do, what do they have, 100, like 90 questions on this review? I probably have time for like 8 or 9. And so, yeah, so I have to go pretty straightforward, I think. I don't know if that makes sense, but so why did I bring that up? It's just an important part of using the mean value theorem. You got to make sure it applies. And sometimes we overlook that, that it's differentiable and continuous. So I'm looking for suggestions, questions.
Can we go through one where we find the extrema?
Find extrema? Sure.
Yeah. Okay, thanks.
So let me see. That would be, well, that would be there's a possibility there. I think we got to move to the left a little bit here. Yeah, still more. Whoa. Wow. Asked me to sign in again. Wonderful. Okay, now we got to increase size. There we go, 43 to 48. Find all relative extrema. Okay, that looks like the section you're talking about. So let's take a look at number 47. 47 is one of those. Find all relative extrema. Use the second derivative where applicable. So I'll try to explain what what's meant there. All right. Well, first of all, extrema, as you well know, occur when the first derivative is 0. So that's going to be our top objective. Take the first derivative, set it equal to 0, and find out when that is. So I've done that on the left side here. 2x plus 18x to the negative 1. Derivative 2 minus 18x to the negative 2. So that's 2 minus 18 over x squared. Add 18 over x squared to both sides. Cross multiply. And you come up with two values for x where the first derivative is 0. Plus and negative 3. Now, here's where the second derivative might come in. How do you know which of those is which? You know, of that plus 3, are you sure that, do we know if that's a high or a low, or what's going on there? And that's where the second derivative can help you out. So here's, I just copied the first derivative over here up in this box to my, and then I took the second derivative, which is just positive 36x to the negative 3, rewritten as 36 over x cubed. Now, here's what this can tell us. What's the second derivative at those two critical points we found? The second derivative at 3, well, 3 cubed is 27. 36 over 27 is positive. What does that tell me? The curve is concave up at positive 3. And if it's concave up, did I draw a picture? Yeah, it's concave up. And so that must be a relative min. It's got to be sitting at the bottom. And on the second one, what's the second derivative at negative 3? Negative 3 cubed is negative 27. 36 over negative 27 is a negative, so that must mean the curve is concave down, and that means, so the negative 3 point is a relative maximum. So I wrote that out right here. Plus 3, concave up, minimum, relative minimum. And negative 3, concave down, so it must be a relative max. So that's one way the second derivative can be used. I guess you just asked me for extrema problem. So, okay. I think... yeah. Did you have any follow-up on that?
Not really, but if you're looking to find the ordered pair, you just plug those critical points back into the original function, right?
That is correct. If
okay.
You wanted the ordered pair, you'd have to say 3, and then you'd have, let's just do that.
Okay.
So first we have positive 3, and when you plug in positive 3, what do you get up here? The second part would be 6. 3 times 2, it'd be 12, right? F of 3, did I do that right? 2 times 3 is 6, and 18 over 3 is also 6, and 6 plus 6 is 12. And then what's f of negative 3? Negative 6, so it's going to be negative 12. So there's your ordered pairs, your two of your two critical points. Take a look at that one. 2x plus 18 over x. So what were our 2 points here? 3 comma 12. And what did we say? That's a relative min. And if we look at the graph, sure it is 3 comma 12. That would be right in here. See how that's a relative min? And then the other point -3, -12, and we said that was a relative max. Yep, there it is, -3, -12, and that's a high point where it's concave down. Another question? Anything else you want to talk about or ask about? Not hearing anything. So I guess what you're saying is, at the moment, that's where we are. You can certainly contact me in the meantime if you want to, and of course, you've got the tutoring session possibly that you could attend, but don't hesitate to send me a problem or ask me a question electronically, or call me. Okay, well then, thank you. It's good seeing you guys electronically. Have a good rest of your day.